I will switch off my video. I'll share my notes. Okay. Okay. So let us, let me quickly recap the basic principles we have discussed so far, right? So we discussed random walks. Okay. We discussed random walks, and before I go into more details, let's also revise the sort of broader conceptual framework in which sort of we are trying to think through, right? So I made this sort of a three-dimensional diagram. By the way, I don't know if it exists in any book or so it might be totally nonsensical. Okay, so this we were representing as time, this we were representing as space. Okay, this we were representing of levels of organizations. Okay, now at this origin you can think there is no space, we have ignored the space entirely, and then we are looking at individuals. Okay, and then as we move up along this hierarchy of organizations, we will have groups, we will have populations, meta-populations, communities, right? And finally, we'll have ecosystems. And by and large, in ecology, we want to understand properties of all these hierarchical levels of organization across space and time. Okay. Sometimes we may take a static picture. We want to know, for example, how are communities structured in space. Okay. Or we may even ignore the space as well as time, and we may just want to see, if I do some averaging, how are communities structured in space, some kind of an average of space and time. And we may think how populations change over time, ignoring space. But we may also think how populations change over time while accounting for space. So there are all different sort of levels of approximations we make to sort of study various behaviors in ecological contexts. And much of the previous course, as I mentioned, either in ecology or in the ecological or the evolutionary context, were how populations change over time, right? And also how communities. Of course, I was looking at really, really simple communities in the context of competition and predation. How they change over time, what are the properties of equilibrium. So that's what we studied in the VC 101. So, but now we are in this course, we will cover much bigger area in this sort of hyperdimensional conceptual frame. So we began with individuals, and we began, if this is one generation time scale, we began looking at what happens to individuals within a very short time scales, much less than their lifespan and generation. And we were looking at in the context of foraging. And in some contexts, we thought that random walks are a great starting point to think about properties of how animals move in their landscape. Okay. Okay. With that sort of broad description, we defined random walk. So random walk we defined as the location of an animal at T is given by the previous location. Okay. Plus some, plus 1 unit with probability half. Where this happens probability half, or it could be -1 with probability half. For the sake of simplicity, we studied the one-dimensional random walk, but the assignment has, two-dimensional generalizations as well. Okay, so we and the crucial part about this random walk is that the events, broadly speaking, events or the states of the system are probabilistic in nature. So unlike the course we studied in the previous semester, where populations changed in a deterministic manner over time, here every event is a stochastic event. So that there is a probability plays a really, really important role. And these kind of, variables where there is a variable that changes randomly over time. Okay, we usually call them stochastic variable. So in all these, there will be mathematicians here who will probably cringe at the level of simplification and lack of rigor on the mathematical aspects in this course. I really request you to excuse me. But I'm more than happy to recommend you all the necessary materials if you would like to, understand this in a much more rigorous way. Okay. And in fact, it is quite useful to understand in at least at a level of rigor that physicists study. That actually is quite useful. I would say, in fact, it's almost an optimum level for studying many of this stuff. If you're interested in, mathematical biology type of areas. Okay. So, now let's step back a bit again. Think about stochastic variables. Whenever we have stochastic variable, there are a few things we want to, calculate, sort of, as a standard practice. What are those? Those are mean, variance, and correlations. Okay, so all of us understand mean and variance fairly well. We have been studying this from high schools, right? Correlations are something we hear a lot, and it's I will in the future classes I will come to this regard, defining clearly and also using it in our contexts. Okay, but I think I'm assuming that all of us have a basic understanding of what these quantities are, and I have also given you the definitions last time. Okay, and these are the first set of things that we would study. But do they themselves completely characterize stochastic variables? The answer is no. You can have two different types of stochastic variables, whose mean might be same, but the variance can be different, right? Whose mean and variance can also be same, but they may have a very different underlying structure. Can somebody tell me what could an underlying structure be that is different, despite having mean and variance same?
The distribution.
The distribution. That's a very important thing. What we call distributions. If we are looking at discrete random variables, probability mass functions, we call them probability mass functions. If they are continuous, we call them probability density functions. Okay. So we have these two types of mathematical distinctions. Okay. So now for the case of random walk, which we were studying in the case of context of how animals move and how they forage, we have calculated so far mean and variance. Do all of you agree? We have calculated mean and variance. So what was the mean of the stochastic variable xt? That was same as x0, right? The initial location. And if the initial location to be 0, this turned out to be 0. Okay. This is the mean value of the state variable. Or if you think of mean displacement, if we define d as displacement, then mean displacement will be 0. Okay, that's the mean. Okay. Now, what was the property of the random variable xt in terms of the fluctuations or broadly variance? We calculated something called mean square displacement. What was that? That was xt minus x0 whole square, right? So basically this measure xt minus x0 measures how far you are from origin at after time t steps, right? Now, and then you square it and then you do an average. And what it does is that the fact that you're squaring means that the positive and negative values don't cancel anymore, they won't add up. So this is really a measure of the spread of the random walk random walker from the origin or the starting point. Okay. And what we showed was that this was basically proportional to or equal to sigma square times t, where sigma square was the variance of the variance of step length. Is that right? Is that right? Okay. So this is what we found, and if we did not look at different step length, sigma square would be for the exact random walk defined here. Sigma square would be just 1. Okay. So we have found the mean. We have found the variance. We haven't yet calculated correlations. We haven't yet calculated distributions. Okay. Any questions so far before I move forward? And before we move, we also, the assignment also has generalizations for 2 dimensions. Okay. I hope I had no problems with that. I think there were, I gave you how to generalize this. The code I showed you last time in the class, where you were looking at the visualizations. That was a 2D generalization. And in the assignment, it's the same exactly mathematically equivalent thing, except that I wrote that in a slightly different way. Okay. Is that part clear to everyone? Do you have any questions? Okay. So we will, for the mathematical aspects of it, we will stick to the 1D only because the mathematics will be a bit easier. Okay. So we have now understood mean and variance. What about now distributions? I'll come to correlations a bit later. Okay. So let us look at distribution. Now, what do you mean by distribution? Okay. Let us think of this in the following way. Right. Now, you saw that, let's think of this. This is the x axis, is the location where the animal is moving. This is the origin. This is where, let us say, animal began its movement. Okay. This is where the animal is present now. After one time step, what happens? Animal can come here, right? Or could have come here after one step. Now, after 2 steps, what could happen? Animal could go here, or animal could have come back here, right? That's one point. That's one possibility. But this is the only possibility. There's an entirely different possibility, right? Now, the 2 possibilities that I just told you now, assume that the animal had hopped on to the right side, right? Now, of course, it's equally likely that the animal could have hopped on to left side on the one-dimensional, world. If that was the case, now there are 2 possibilities. Animal could have hopped on here. Animal could have hopped on back to the origin, right? So do all of you agree with this? Now let us ask a very simple question. After 2 time steps, where could the animal be? After 2 time steps, where could the animal be? Okay, now intuitively, it's now fairly clear that animal after 2 steps animal could be in which places? It could hop here, and once it hops here, it has to come this way or this way, right? Okay, so after 2 steps, possible locations are -2 and 0, right? For an animal that hopped left the first time, the final possible locations are -2 and 0. What about the animal that hopped to the right? That could have gone further or could have come back. So therefore, it could be in 0 or it could be in 2, right? So basically, there are 4 possible locations that the animal could have been at the end of 2 steps, right? Now, what is the probability? Let's ask this question. Probability that the location of the animal is -2 after 2 time steps. So this notation basically means that what is the probability that x is equal to -2 at time step is equal to 2 after 2 hops. What would that be? Only one of the, we know the basic definition of probability, right? It's only one of the 4 possibilities. So 1 by 4. So likewise, what is the probability at x equal to 2 at time 2? That would be, again, only one of the 4 outcomes would give us a location at 2, positive 2. What is the probability that animal was at origin after 2 time steps? That would be, can somebody please answer?
Half.
Half, right? Because there are 2 possible outcomes that could give, take us back to the origin, right? So 2 by 4, that will be 1 by 2. What about the probability of reaching 1? After 2 time steps?
That'll be 0, right? Because you can't.
0, exactly. Okay. Likewise, probability of being -1 is again 0. So after 2 times, this is a very, very simple, example, assuming discrete time, discrete space, and so on. This is what happens, right? So we can actually represent this in the following way. So you can represent in the following way. Sorry. So let us say we are again here. The x-axis is x. This is the origin where the animal starts. So I can represent it in the following. This is half. This is 1/4. This is 0 again. This is 1/4. It's basically a histogram that we're all familiar with, right? Except that it's normalized. That way, if I add all these 3 boxes, evaluate all these 3 boxes, it would be 1/4, half plus 1/4. It will actually add up to 1, right? So we call the y-axis of this graph p x t, and the x-axis will be x. And this is for t is equal to 2. So this graph is for t x is equal to 2. This is clear? Okay, this is called the probability mass function, but technically in this case, because x is a discrete variable, so is t. Okay, so primarily x, because x is our the state space in this model, in this random walk model. Okay, now we can ask the following question: what happens after some arbitrary number of time steps? If I ask the same question after 10, how do you think this will look like? Any guess?
There'll still be a quite large gap at the top, middle, and each of the even values will still be high, and I think each of the odd values will still be 0.
Because, okay, is that fine with everyone? Okay. So in fact, you can actually, turns out that you can mathematically exactly derive this. Okay. So this is same as this problem. Interestingly, this actually relates to the first question in the assignment, by the way. Location of animal randomly moving after, let's say, t steps. Let me know if you think it is right or wrong. Okay, is actually same as I'm not saying that the location is same as, but this problem is basically mathematically equivalent to number of heads you obtain after tossing a unbiased coin. So t times. Do you agree? So basically, when I'm doing this, what I'm doing is I'm assuming that moving left could be thought of as tail, moving right could be thought of as head. Okay, and we can even, if you can assign a numeric value of t is equal to -1 and r is equal to r is equal to +1, then the problem is basically identical. So the number of so although I have written number of heads here, so the location of the animal, right? Location of the animal after time t, right? After time t, that is basically is equal to number of heads minus number of tails. Is that right? If the number of heads are equal to number of tails, the location would be at origin. And if the number of heads far exceed the totals of tails, then you have moved. It's equivalent to having moved right. The number of tails are far higher than the number of heads. It's equivalent to having moved to the left. Do you agree with this? Mathematical equivalence. I hope you do. Okay. So basically, the random walking problem is basically nothing but the mathematics of coin tosses. Okay. And for those of you who still remember some of your probability classes, you will quickly note that binomial distribution comes prominently, in this when you do a coin toss. Okay. Okay. So in fact, what you do find is that if you toss a coin n number of times, what is the probability that k of them will be heads? Let's ask this question. Probability that k heads occur in n tosses. What would that be? That's actually n choose k times half power. Is that right? Okay. So if you can actually use this to sort of make a mapping back to xt. What is the distribution of xt? Is something it is actually possible to say n tosses now becomes t steps. N tosses are basically t steps that the animal has moved. Okay, what are k heads? What do k heads mean? K heads are equivalent to, what does k heads mean? K right turns, right? K right turns. Now, what we also know is the number of right turns and the number of left turns must add up to total number of turns, right? So if you use that information, you must be able to write the exact distribution for how the probability of the animal is at location x after time t. But anyway, you don't have to worry if you understand all the mathematics of it. But the point is, as somebody said, if you just think about intuitively now, you have this graph. If you were to now plot it after 10 time step, how would this qualitatively look like? Or maybe even longer. Okay, let's say this is origin. Let's just do it step by step to make sure we all are on the same page. P of x of t. After 10 time step, as somebody said, the largest frequency will be where, largest probability will be still at 0. Okay, so I won't worry exact numerical values. No, the maximum will be still at 0. But what's the maximum distance the animal could have gone on the right side? After t steps, assume discrete only. What's the maximum the animal could have gone? One possibility is it actually makes right turn at every step, right? So by the way, I shouldn't be using right or left. Right or left is truly to our the way we are seeing on the board, but technically it's actually one-dimensional walk. Okay, so please be clear about that. Okay, so if every direction of the movement was towards positive x-axis, the animal would have gone to maximum of t steps on the right side. Is that right? Likewise, if every step was to the left, it would have gone to minus t. Is that right? But what would these probabilities be? A probability of every step being right is what? Its probability is half, 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 half. So this probability will be a very tiny probability, which is given by half power t. Likewise, this would also be a very tiny probability where it's half power t. Okay. So that's the maximum distance you could cover after time t steps. Now, what about some intermediate step here? So now you can use the binomial distribution and do the mapping as suggested. You should be able to get that exact answer. Okay, but will this be more than the, let's say, t? Let's say we are on the odd, okay, not on the even now. Where we have t. Let's assume that t is even, and therefore we're looking at an even number of steps here. So what would that be? Will this be more than this? Yes, because the reason is, there are many more ways to arrive at any intermediate point compared to the furthermost point. Okay, so this would be some value here. I don't know what exact numbers, but we can calculate that using the distribution. It will be like this. Likewise, it will be like this here. Okay. This is how the distribution will look like. Any questions so far? After these steps. Okay, and in fact, this distribution will indeed be a binomial distribution. Okay. Now, let's imagine a case and the number of steps are really large. Okay. How do you think this will look like now? Now, which means that the between minus t and see when we did just two steps, right? There were just five possible states. 1, 2, 3, 4, 5. When we have t steps, let's say t being 10, we have 21 possible locations the animal could have been, right? So from 5, we have gone to 21 possible locations now. Okay, minus 10 to plus 10, including 0.
Am I audible?
Yes, you're audible. Yes.
Yeah, I just wanted to. So it's not 21, right? Because in 10 steps, you can't reach 1 and minus 1.
But no,
they have to be the same parity.
Yeah, what I meant was 21 possible locations, but some of them will have 0 probability, right?
Okay.
The intermediate ones will have 0 probabilities. Huh? You're right. Yeah, because we're doing a discrete random walk right now. Okay. Now, if t was a much bigger, much larger number, the number of possible states between minus t and t will be 2t plus 1. But you're right, that it won't be 2t plus 1. Half of them will not be available. Okay, it will be of the order of t only. But the t is now really large. So therefore, the distance between the two consecutive possible states would have reduced dramatically, right? So in fact, what happens, I'll just state this without any sort of proof, is that as t increases, and you can now ignore the fact that when t is very large, the distance between the two steps compared to the fact that they could have actually moved really large distance will be really tiny, right? So this binomial distribution will effectively start to look like a Gaussian distribution, what's also called normal distribution. Okay, so origin being 0, sorry, this is not the best graph that you will ever see of normal Gaussian distribution. But this is my really bad attempt at drawing it. Okay, so that's what we expect. Okay, this is the probability at time t, which is really large. Okay, do all of you get an intuitive sense of this? Do you have any questions? And the important thing is this distribution is changing with time. This distribution was a very, very narrow distribution at 0 at t is equal to 0. Right? At t is equal to 2, I showed you what happened. At t is equal to 1, it would be now sort of just 2 bars, 1 at minus 1 and plus 1. And now at t is equal to 2, it now the 3 bars, minus 2, 0, and 2. And I showed you what happens at an intermediate. And now it's really a large distribution for t being very, very, very large. Okay. So the means, now what does the mean displacement and the mean square displacement mean in this context? The mean displacement basically measures, basically the mean of this distribution now after time t steps. Okay. What does mean square displacement measure? Mean square displacement measures the spread. And the spread is increasing with time. The spread of this distribution is increasing with time. And that's what the mean square displacement is measuring. And we showed that basically mean square displacement is equal to variance of this distribution. Okay, so what we have basically is random walk, basically in that sense, leads to a time dependent probability distribution. Okay. And what is the mean of this distribution? Mean of this distribution is 0. Mean represents the mean displacement of the animal. What is the variance of this distribution? Variance of this distribution is basically mean square displacement of the animal, which we have shown is proportional to the time. So it's a time dependent variance. So every, whoever has studied statistics so far, you would probably have encountered a distribution which has constant mean and constant variance, right? One of the fundamental assumptions of most statistical analysis. But what we're really seeing here is that a distribution whose mean is 0, time doesn't depend on time, but the variance, however, changes with time. Okay. The variance of this distribution, where the animal could be after time t, actually nothing but the mean square displacement that we computed in the previous step. Okay. So this is the intuitive picture. In the next page, which I will start now, I'll wait for a few seconds to have you ask any questions. We'll formally, slightly more mathematically derive P of X of T. Any questions?
So won't this be the variance only if the mean itself is 0? Because otherwise you'll have the MST with respect to like the 0 or the origin, and since you're starting at the origin, then the term cancels out for the variance. Otherwise, your variance will be xt minus expectation of xt, the whole square average. Here,
there's no.
Yeah.
So MSD does subtract x0, right? MSD is xt minus x0 for square. So x0 need not be 0. It could be anywhere.
So in this particular case, the MST is the variance only because the modulus, the expectation of xt happens to be x0, right?
Yeah. That's not a property I have forced though, right? It's a property of the random walk I have defined.
Yeah. So in general, though, MSD is not necessarily equal to variance.
In general, MSD, yeah. So I'm not talking about in general. I'm talking about the random walk that we have defined. In fact, what I have defined here, I have defined not a random walk. No, I have defined what's called an unbiased random walk, right? Just like an unbiased coin toss. Okay. In fact, what I will ask you to do in the work today, which as I have already said, will not be graded and all, but I would still like you to work out, is that I would like you to think of a biased random walk where some of the questions you are raising become very, very important. Okay. So where xt will not be in an unbiased random walk, average of xt will not be equal to x0. Okay, then you can actually see what happens. Did I ask that question in the assignment, by the way? Biased random walk?
Yeah.
Yeah, I have, is it? I've forgotten what. Okay. So you already would know then. Okay. Yeah. So I will ask you a very different question. I have already forgotten what's there in the assignment. Okay. Any more questions before I go forward?
Yeah, I was just thinking, since the random walk is a time dependent distribution, can you also formulate it as like Poisson distributed, like the probability of finding the organism at a given place would be Poisson distributed, right?
Can you repeat your question? Why should it be a Poisson distribution?
It's like trying to find the probability of success after a given number of trials would also be Poisson distributed, right?
That is true. So if you have a constant rate event that's happening, right? And if you wait for some time, if you have a time interval where you wait, the number of successes will be a Poisson distribution, right?
Yeah.
That's where the Poisson distribution comes. So maybe here the equivalent, what quantity will be Poisson distribution here? Some quantity will be, but not the one that I have defined though. So far, not the one that I have defined, but some quantity can be Poisson distribution, right? I think maybe
the probability of finding an organism at a given place would be Poisson distributed, right?
No, that would be Gaussian distribution, as I said. But in some limit, they all become same. Poisson, Gaussian. In some limit, they all converge to Gaussian. So, but I think there'll be some specific instance where what you're saying could be true. For example, animal has some rate of random movement, right? Now the question to ask would be how many steps does it take in a given time interval? I think that would be a Poisson distribution. I don't think they say about the location as much too, but maybe I'm wrong. It might be a possibility of even saying it in terms of location.
Okay.
Okay. Yeah. I'll think about it. But I think usually Poisson distribution, I think of it as the number of successes as you define, the number of events of your interest that happen in a given time interval, right? So I have thought of it as usually in the time dimension. There might be some way it may also be thought of as a spatial Poisson distribution, but I don't know right now. I'll think and get back to you. Okay. But it's not evident to me right now how. Okay. So now let's do the following. Let's ask the question that whatever we have done intuitively so far, let us do it slightly formally and mathematically. Okay. P of x. Let's define P of x of t is the probability density of random walker at x at time t, where x and t are both continuous. Okay. Now this is we are making a huge jump here from what I have defined so far is a discrete space, discrete time, random walk, right? So assume that the one time unit one space unit I mentioned in the very early definition of random walk, okay, it moves plus 1 unit, right? Assume that 1 unit could be arbitrarily small, delta x. It did not be 1 unit. That's the first assumption, and it could be continuous. Right? The second thing is the 1 unit in time that I am defining here is also an arbitrarily small or large. There's nothing discrete about it. So you can replace the 1 in time here by delta t and the 1 in space by delta x. So then what we have is a continuous time random walk. Under that assumption, how is this probability density function changing over time? That's what we would like to understand. Okay. So how do we understand this? Again, draw the line. We have x. Okay. Let's say animal has some probability density at x at time t. Okay. There's a probability density at time t. we would like to know what is this. So there is some value for this right now. Probability that the animal is at X at time T. Okay. There is some value. We want to know how does this value change. That's what we would like to understand. Okay. So now just think about the following. What are the ways by which the probability will reduce? What are the ways by which the probability will increase? Okay. So to understand this, so basically, of course, you have a baseline probability. If nothing happens, if the animal is not even moving, this will be right now. The animal is not moving at all. Probability of that animal will be at X at time T plus delta T will be same as probability density at X time T if the animal was not moving. But however, the animal is moving. So that means there are some factors of the animal movement that will enhance the probability of or the animal being now at X. What was that? If there was an animal at location X minus delta X, and if it made a jump towards X, if I made a jump delta X towards X, that will contribute to an increase in the probability. Is that right? So that is probability that animal was at X at a previous time step times the probability that it jumps. Sorry, I made a mistake. Do you know what it was? The increase happens from the other location, not the current location. The current location is already accounted for here. Okay. The location to the left, there was an animal there, and at a previous time step, and that animal now jumps plus delta X. In such a case, what happens? There is an enhancement of probability here. Does everyone agree with that? What's the other way that the probability can enhance? I've given a hint by writing something there.
It comes from the left.
I mean from the right. Right? From here to here.
From the right, yeah.
It jumps to left, but from the right. Okay. The second term, other way it can increase is probability that at X plus delta X, there was. So, I'm using loose language here. So it doesn't mean that the animal was there. I'm just measuring. There was some chance that the animal was here at time, at the previous time step, and then there is some chance that again it jumps. Probability that it jumps minus delta X. Is that right? Okay. Okay, these are also called transition rates. Usually, the probability of, so in a more general sense of random variables, X need not be location, right? X could be some state that you're interested in. So basically, the jump from one state to the other, those are all called transition probabilities. Okay. Now, what is this transition probability? An animal being at X plus delta X moving to X. What is the probability? Now, it depends on the rules that you define for the random walk. Okay. Now, the rules that we defined, if you go back here, was it? We assume that the one can be replaced by an arbitrary small delta X, right? So now once the delta X is fixed, there are two possibilities any animal will do. It could go to, from its current location, it can jump positive delta X or a negative delta X. And both of them happen with equal probability, right? So therefore, what is this probability? Let's say this blue jump here. What is the problem? What else could have happened here, by the way? If an animal was at X plus delta S, what else could have happened? It could have jumped to the right, which takes it to 2 delta X, right? There were two possibilities. Only one of them is what we are interested in. So what is the probability of this then? This probability will be half. So likewise, this animal on the left could have come to our location of interest, but have also gone to the exactly other direction, x minus 2 delta x. So what was this probability? It is half. And what is the probability that we are interested in? That is to the right. Okay. So now that explains us. So now let us write this down. So this is, so therefore, P of x t plus delta t P of x minus delta x t minus delta t minus delta, sorry. Oh, sorry, I'm making a mistake here. None of you have corrected me so far. What's the mistake I have made?
There also needs to be stuff leaving the thing. So you'll also have
absolutely. And then the stuff that is leaving. Okay, let me just erase everything. Okay, it's so easy to erase. Okay, I'll just erase everything. Stuff. There's one more mistake that I have made. What is that? Of course, there's stuff leaving. But before that,
shouldn't there be just 2 time points in the equation?
So see, I'm looking at t to t plus delta t, right? So everything on the right hand side must have been t. Okay, but I made a mistake here. So it's just is that clear to everyone? It's just, at time t, there are 3 possibilities. The animal was already present, that is this. Animal was at a left location, it jumped, that is this. The animal was at the right location, it jumped towards x, that's this, right? So this has to be t, not t minus delta t. And what's the last thing? Animal was at x, okay, and then it jumped towards where? It jumped to one of the 2 directions. So it could have gone from here, animal from here has left to either here or here. What is the probability? That's actually 1, right? I mean, given the way we have defined animal, probability, random walk, it has to go to another 2 locations. So this probability will be 1. Is everybody on board?
Yes.
Okay. And again, remember that these 2 probabilities, they are both. This what did we agree? This was actually is equal to half. This was equal to half. Okay. So technically, we can just cancel the first and last term, but I won't do it. Okay. Now that we now have the full equation. Okay. So what I will now do is any good person who knows calculus does, we want to know how the probability density is changing over time. Therefore, I will take this to the left-hand side. That's the left-hand side I'm interested in. And what's the right-hand side? That is half times. I'll take half as a common factor now. Probability that the animal was at a location to the left and then jumped. Probability that the animal was at a location to the right and jumped. And the animal was there and then jumped. Why is it 2? Because I have taken this half as a common factor. Okay, so this is the right hand side. This is the equation. Is that clear to everyone so far? Any questions? Okay, there are no questions. Please ask me questions because we will be doing more algebra now. Any doubts, please ask. Okay.
So, I have one. So are we still treating these as densities functions or?
Yeah, we are treating as densities because the way I defined, but to be very, very honest, the right way of doing it is the way Einstein did. I can actually send you his exact steps. If you can understand a few integrations, it's really beautiful. It has no loopholes in the way it defines everything. But whatever I'm doing, there are lots of mathematical loopholes here. So but I think for this class, this is good enough. Okay. So why did Einstein come suddenly? Because the first person who actually wrote down the theory of random walk was Einstein. Apart from a person named Smolchowski, they use slightly different formalisms. Smolchowski was the one who then developed the entire field of stochastic processes. And for Einstein in particular, the motivation was, of course, physics, but there was a very interesting biological context you may have heard of. Okay. As you may know, random walk is also called Brownian motion. So Brown was a botanist in 1830s who was studying how pollen is moving when suspended in liquids. And when he observed this, very, very, very jiggly motion of pollen particles, he thought that might be a sort of, spontaneous motion that represents life. But then, but unfortunately, what he also found was that, even dead pollen exhibited same sort of motion. So, but what exactly was that motion was Einstein, went on to describe. And so basically random walk has origin both in biology and physics. Except that here, in the way we are defining random walk, we are ignoring the medium that the particle is in. So, but that doesn't really matter much because the rules of how the particle is moving is still random. Okay. So the next step. Now let's do. So we have bunch of stuff on the right hand side. Now I'm going to assume that Taylor series of two variables. Okay, what is that? So it's P of X of t. I'm expanding this around X with delta X being the perturbation. Okay. Okay, so there are more terms, but I'll only write the two leading order terms. Likewise, I will write this. So instead of perturbation being negative, it's now positive. Okay. So what you have here, right, is a summation of these two terms, the first term here, the second term here, right? If I add them, what do we get? If I add this and this, so 2 times P of xt, these two terms just add up, whereas these two terms cancel out. We have 0, and then these two terms again add up. Delta X square. Again, the next term cancels, and I'm going to ignore the rest. There are 4 order terms which I'm going to ignore. Okay. So the summation of the first two terms of this right hand side is equal to 2p of xt plus 0 plus delta x square this. Okay. So let us substitute this in the equation here. You can clearly see that the 2pxt we have gotten gets cancelled with this 2pxt. So what we are basically left with is this term. Is that right with everyone? If I'm adding these two and then subtracting the term here, we are actually left with is equal to half is still there, delta x square 2px square x square. Is that clear with everyone? Okay. So we have simplified the equation substantially. Of course, there are more terms which I'm going to ignore, order 4 terms and so on. And then the next thing we want to do is, to make it mathematically more convenient, we divide the left-hand side by delta t. And then the next thing I will do is to take the limit as delta t goes to 0. So the left-hand side now becomes dou p by dou t, rate of change of how this probability density function, right? Because we had a probability density function that is changing over time. How does that change? That changes in the following way. Delta x squared by 2 delta t, because delta t comes from this division, okay? So now delta t comes from here with both the delta x goes to 0 and delta t goes to 0. And then we have dou square p by dou x square. Okay. So what we have is the rate of change of this probability density function is equal to some coefficient here times dou square p by dou x square. So let us think about this. What is this, by the way? Delta x square by 2 dt. Now that's a bit hard to understand. If both delta x and delta t are going to 0, what will happen to this, by the way? Delta x square goes to 0, delta t also goes to 0. But what happens to the ratio?
You get 0 by 0.
I get 0 by 0. Huh?
El Hospital rule will begin up here.
What does it say?
That like we should, because in such indeterminate situation we should differentiate and then put the limit until.
And then what happens? If you do, what happens?
Until we get.
So if you do that, what happens?
There. So then we get, okay.
It's a bit tricky because in those, there are 2 different terms here. Delta x and delta t are 2 different things, right?
Yes.
So they're not, usually when you apply those, you have some f of x by g of x form, right? That's what you do when both f of x and g of x goes to 0. That's when you apply. So here they're actually independent terms. Okay, except that they're actually not independent. So this is very, very tricky, and let's think about this. What is this mean square displacement? Mean square displacement was xt minus x0 displacement, right? Was proportional to time, right? But this could be thought of as delta x over some delta t, right? So what is this, by the way? What do you expect this to? If this event happened, if a displacement delta x happened over at a time delta t, what will this be equal to? For a random walk?
So that would be sigma square.
Let's forget the sigma square for the time being. Yeah, sigma square, you're right, okay. Times
delta t.
Delta t, right?
Delta t.
For random walk. That's what we have derived, no? And when we derive this, both the spatial jump and the time jump were arbitrary, and that could have been infinitely small too, right? And if so therefore we know this is true, right? For random walk. If you apply this to this, what happens? What will be this ratio, delta x square by delta t?
It goes to a constant.
It goes to a constant. When this implies that this goes to a constant, and that constant is usually denoted by, some people denote it by 2d, some people by d. Okay, so you have this. So how many of you have seen this equation before at some point of time? Has anyone seen this before?
This fixed law.
Yes.
Yeah, this is it relates to fixed law. It's called diffusion equation. Okay, does it make sense though? Do you now know the origin of fixed law in some ways? Okay, so this is really interesting. So this is also called diffusion equation. This tells you how things spread at the, so think of, no, this is very important to think, okay? This is, when we started off, we were talking of jumps at very fine time scales and very fine spatial scales. That's really important to understand. So, delta X, delta T are really, really tiny. That's when we started off with the random walk. And here you should think of X and T as over large spatial and time scales. Okay, so what this means is that the random walk, at fine scales leads to diffusion at what we call macroscopic scales. And this is really beautiful in many, many ways. We, at some point of time, I'm assuming you may have heard about diffusion, right? We all use the word diffusion literally somewhat casually too, right? But when we say something is diffusing, what we are really meaning, let's say if we say that, if I drop ink, forget animals for the time being, if you drop ink in a very slowly in a medium, and we say it diffuses, what does it really mean? If it is truly diffusing, what must be particles doing under microscopic scales? Every ink particle you have dropped must be doing a random walk. Is that reasonable to say? Okay. And when we say that, certain chemicals diffuse from one medium to other, what we mean is that, actually at every spatial location, every particle is actually doing a random walk. But at the macroscopic level, what we observe is a diffusion. Okay. And this is the link between, beautiful link between random walk and diffusion. Okay. And what is also called diffusion equation. Okay. And now, although we started off thinking of it as a single particle, but remember that, imagine a scenario, we began the entire discourse of random walk with a single animal standing in location X, right? Now, one way to sort of make better, easier connection with this is, imagine there are a large number of animals standing at one location at time T, but now if just they begin to move randomly over space. Okay. Okay, so everybody was, this is X. Let's say, imagine there are lots of individuals at location 0, lot of individuals here, and then they all now begin to move randomly. Okay, so this represents the, let's say, number density.
So does the effect of collisions cancel out?
So we are assuming, we are ignoring those details here. We just, as long as the collisions themselves also effectively lead to random walk, okay, then we are describing what happens. If you think of a physical system here, okay. So if you were to assume that after collision and after any interaction that they might have, they're still moving effectively randomly at each point in time. Imagine there are lots of them at time T at t is equal to 0 at location x0. What really is happening is that over time, they become like this, they spread out and they diffuse. This is, t is equal to 0. This is t large. Okay, you can think of it as large number of individuals random walking and therefore leading to diffusion of the concentration. That's one way of thinking about it. Another way of thinking about it is, there is a single individual who is at location origin at time t is equal to 0. Now, what is the chance of finding an individual after time t? How is that envelope of probability changing over time? And the answer to both the question is exactly the solution of the diffusion equation. Okay, that follows the diffusion equation. Is the intuition behind it clear? It's okay if you don't fully understand all the algebraic steps, but is the intuition clear? And the fact that there is actually a connection between random walk and diffusion, I'm just curious, Did some of you already had done this derivation at some point of time? Maybe in some courses you may have done. If you have done some, maybe some course in chemistry, maybe some course in physics, some course in fluid dynamics, you may have come across this in some form. Okay, so that's where we are today. Okay, now,
Sir,
yeah,
I
go
had
ahead. Yeah.
Yeah. So when we began the derivation for the diffusion equation, we had made a couple of assumptions, right? For example, fixed step length and no waiting time, like as in at every time step delta t, the particle is definitely going to make a move either to the left or right. So is the equation that we derived, is it going to be invariant to those assumptions?
It is not too sensitive to many of those assumptions. You're right. Yeah. Yeah.
So is in a
It's
sense,
actually a lot more than the assumptions I made. The final diffusion equation is lot more robust to the assumptions that I made here.
So in a sense, can we say that if we change the dynamics, as in if we change these assumptions a bit, like the value of d is going to capture those changes, and qualitatively the equation is going to remain the same?
True.
Is that how it?
True.
Okay.
True. Within some limits. There has to be some. For example, I can tell you what assumptions can be relaxed. For example, we assume when writing the first equation, right? This equation, right? We assume that in delta t they move delta x steps, right? So this delta t need not be a deterministic time step. Okay, this delta x need not be a deterministic time step, deterministic spatial step. They could both have distributions, and as long as they have finite variance, the results will be true. Broadly, there will be some caveats. I think broadly what I said is correct to a large extent. As long as they have finite moments, the results will be true. Okay, that's a good question. Great question.
I have another question.
Sure.
Can you?
Hey, it actually really helps me if you tell me your name when you're also asking the question.
My name is Gaurav.
Yeah, sure.
Yeah, so could you go over again why you can replace, like what the justification is for replacing the limit by the average?
So this just follows from the derivation we did for the a random walk, right? So in random walk, we know that the mean square displacement is proportional to the time over with the displacement that happens. Is that right? So that's something we know. So for example, now if I were to look at the displacement that has happened, mean square displacement that has happened over a delta t time step, that will be, this is always true, right? In a random walk.
Yeah, no, for a random
we just derived it.
True, right? Yeah.
And we are deriving and we are starting with random walk here, right? Probability density of a random walker at time. This entire derivation is for random walker.
But the limit is there, no? So delta x is becoming smaller and smaller.
But does this result depend on the step time length in any way? Our derivation of mean square displacement, we assume some one arbitrary unit of time, right? It could happen any unit.
It doesn't depend on the unit. What I'm trying to ask is, so the process of taking a time average of delta x squared is not the same as the process of taking delta x going to 0, the limit delta x going to 0. So why is there a correspondence between these processes?
The basic idea is that if at this stage, if I had somehow forgotten that I had come here up to this point because of random walk, I could vary delta x and delta t independently, right? But the point I'm trying to make is that because it's a random walk, they're not independently varying. Delta x square at every, a limit of delta x is proportional to delta t in a mean square, in a mean sense. And I'm using that fact here.
Okay. Yeah.
I mean, I understand this is a hand-waving argument. May not be a very mathematically very rigorous argument, but this is I agree, this is a hand-waving argument.
So this is Krishna. As a kind of generalization of, as a kind of extension to what Gaurav just asked, how are we replacing the time average of delta x square with just delta x square in the equation? can we take those to be equivalent because it's
so this is not a time average, it's an ensemble average, right? So because the time is fixed.
Oh, right.
Delta T is fixed. It's an ensemble average. And over many such instances, what's the expected value of delta x squared?
In general, though, can we replace delta x, which is in the limit, delta x squared, which is in the limit, with average of delta x squared? Because this one's delta x squared by delta t, the average. And whereas the limit equation has only delta x squared.
True. Which is why it's a hand waving argument. I'm not exactly saying that this is also, there is a limit. Ideally, you should have a mean here, right, to be able to make the substitution and to make my argument very tight, which is why what I am presenting is a heuristic or a hand waving argument. But if you strictly follow Einstein's derivation, that comes out, the average comes out clearly. I think, yeah, I can actually send that. Actually, very beautiful. I can just scan those or take pictures and send them. Exactly the steps that he follows. He doesn't assume, I think, delta x to be constant. It doesn't have to be constant at all. He, I think, assumes that for a given delta t, there is some distribution of the junk. Okay, and then he writes an equation for that, and then he basically does the same type of equivalent of what we do with Taylor series expansions, and then he arrives at the same equation. And for some of you who are interested in more of the physics question, there is a book on statistical mechanics by Reif, R-E-I-F. That the last chapter there is pretty good. That covers in the physics context. Okay. Okay, now, so let me present the next point before we take a break. Okay, we have just derived diffusion equation from. Okay. Okay, we have derived this. So now the scenario that many of us are often interested is something like this, right? An organism is at a given location, right? At time t0. Okay. And then we want to know how this spreads. Okay. How this, given this, how, what is given this now, I want to know how is this, what is the probability density of the animal being at location X after a very long time. Okay, so I will just write down the solution for this. This is called an initial value problem. We have a partial differential equation. I have given you an initial condition, and I am assuming that the X and T can go to infinity. Okay, so this has an exact solution. Okay. So probability that the animal is at location X, the probability density of the animal at location X and T is e power x squared by 2 dt. This is basically like, normal distribution with mean 0 and a variance of dt. Okay, now I don't know how many of you understand this notation. This means that this entire thing, X is a random variable, the location of the animal at time t, that's a normal variable. The first element in this notation represents mean. The second notation represents variance. Okay. And this basically what I'm basically saying is this is an exact solution, analytical solution. If you want to check, you can just insert this back in your equation and verify. I'll just leave it as an exercise. Verify. And to prove this and derive this is a fairly mathematically involved thing, which I will not do here. Okay, so this is what the solution of the diffusion equation is for this specific initial condition. Okay, which is very relevant, which could be in the context of animal movement, how is the animal likely to be at various times in the future. In the context of physics, the example that I gave you, right? If you drop something in the medium, and if the something exhibits a random walk, how is that concentration spreading over time? That will follow this. Okay. So these are some important and interesting properties of random walk. So remember we have described when we go back to random walk, we have understood the mean, we have understood the variance, okay, and we have now understood how the probability density function is changing over time. Any questions before we can take a break now, short break. Is this too heavy for if it's too heavy, let me know. And I have thought of some, although I don't know how many of you are present now, the 19 of you. I think it would be a good idea instead of me, what I was thinking was, instead of me continuing for another 1.5 hours, it might be too hectic. I can actually give you a small exercise, okay? That might make things, more involved. You can actually do things on your own and figure out. So in the meantime, I'll just wait for you to ask any questions.
Hi, this is Rutvij. I didn't quite understand how we landed at this equation from that diffusion equation.
Which equation to which equation?
The one where there's a differential involved, and the equation which looks like a normal distribution.
Yeah, I said I'm not going to derive this for you. There are many ways to derive this.
No, I didn't understand the part where you said that, I don't understand what that sentence means. The organism is at x0 at t equals 0.
That's given. That's called the initial condition.
Okay. So could you just go over that once?
So this is the initial condition. So you remember, let's go back. No, I don't know if you were there in the EC 201 course. Okay.
No, I wasn't.
So you were. So what do we do there? We had a population model like this, right? Of this type. For example, we had x dot is equal to Rx times 1 over, where x in this context meant population density. Okay. And then we start with some population at time 0. It's called initial condition. Let's say x0 is some half of k. K is the carrying capacity. And we start with a population value, which is half the carrying capacity. We want to know what is x of t. How does this change over time? Okay. That's the question that we were interested there.
Okay.
Now, this is an analogous question, but in a probability sense. So, because the animal is now doing a random walk, it is starting at x equal to 0 and t is equal to 0. Okay. And there is no one specific point where it will be after time t, as we discussed all along, right? Today, therefore, we have been discussing, right? Could be many different places. Okay. But not every place is equally likely. Right? So, we have seen you. Go ahead.
Sorry, no. So if I understand correctly, if we change these conditions, this equation will no longer hold.
Absolutely right. Yeah.
Okay.
If you say that the organism was at 0, if there were 2 organisms, one at 0, one at 10, then the solution will change. Okay. But luckily, the diffusion equation is also a linear equation, so you can tell. So it's actually fairly easy to generalize this for those kind of simple cases.
Achha, okay. So is that is it like a qualitatively meaningful thing to describe this initial condition in that case, if ultimately you can sort of still generalize?
Can you ask?
I mean, what I mean is that, so then is this something that we need to sort of worry about in when applying to problems, that this equation applies only for this very specific initial condition? Or yes, it doesn't matter, you can always express it any different initial condition in this form?
There might be ways. I'm not so sure.
Okay.
See, the diffusion equation is very, very well studied. I would imagine that there will be some ways, clever ways to apply this known solution to many other contexts.
Okay.
But now there will be some limitations. For example, I'm not only I'm assuming this initial condition, I'm also assuming something called a boundary condition.
Okay.
I'm assuming that there are actually, you can go all the way from minus infinity to plus infinity. You know, the boundary where the animals can move is infinitely large. That's the assumption I'm making. Okay. Under that assumption, this is a valid solution. So you need to have both this initial condition and this boundary condition. Now imagine a different scenario where there is a fixed boundary, you know, island. Think of an island, right? And if an organism is moving on an island, let's say center of the island, but after distance L, the island ends and the organism will just drop into ocean, okay? Wherever it is. So imagine one-dimensional island, okay? And in such a case, this will not hold true for large enough time scales, right? Yeah. Because what happens is once the animal has fallen in the ocean, you can't come back or it will probably die, right? So groups of random walk are not true anymore. So we call that there's also a name for them. So those kind of boundary conditions are called absorbing boundaries, okay? So once you hit the boundary, you get sucked in. Okay, so that for such a boundary condition, this solution will not be true forever. Okay. It will be true only for some small amount of time. Now there are other types of boundary called reflective boundary. An intelligent organism who doesn't fall into the ocean, let us say, will bounce off from the edge, right?
Okay.
Okay, whenever it hits the boundary, it just comes back. That's called reflective boundary conditions. Okay. I think it's also called Neumann boundary condition, you know, in the mathematics. So, so in such cases, again, the solution will differ.
Okay. But we can nevertheless apply this solution within like some range of values, say for example, depending on
if you're away from the boundary.
Right.
As long as you're away from the boundary.
Right.
Yeah.
Okay.
So for large enough times, you will always hit boundary. That means, you know, there will be limitation to how much you can apply. In many of these cases, you deal with this in two ways. If you are an applied mathematician, you will work hard to find a mathematical solution. If you are somebody like me, I will just use computers and resolve it.
Okay.
Just do computer simulations. Okay. And for large number of problems in ecology and biology, those are computer simulations are the sort of, you know, ones that actually will give us answers because they're so complex.
Okay. Yeah. Thank you.
Okay. Yeah, sure.
Vishu, I have a question.
Sure.
So when we extend this to say 2 or 3 dimensions, the equations would be the same, right? But with
absolutely yes. Absolutely yes.
So there's no effect of like
dimensionality
one
at all.
on the other. Yeah.
Absolutely right. Yes. For both the diffusion equation, just will have additional term, which is a dou square p by dou y square. Okay. And you know, the solution will have another term x square plus y square in the numerator of exponential. Okay. And something about the denominator, you know, the coefficient changes a little bit, but not in a massive way. But the you know, you can because you know when the random walk happens, right? The way animal is moving in the x direction is independent of the way it's moving in the y direction. That's the way we define, right? So therefore, you can assume that those two events are happening basically independently.
Right.
So the random walk in the x direction is basically independent of random walk in the y direction. If I now merge them together, what's the random walk in xy plane? I can take the two distribution and just multiply them.
Right. Okay.
Because they're independent events. Okay.
Yeah. Thank you.
So it's like, you know, take any two random variables. Okay. And if they're independent, then I can multiply their distribution.
Okay.
To know the joint distribution. Okay.
Yeah. Thanks.
I mean, there will be some normalizations you have to do a bit carefully, but that's the basic idea. Okay. So this is where we are. Okay. So, okay, now I don't know. Let me ask you this question now. If I now asked you, just repeat these exact same steps. Okay, start from here. Start from like this. Now, let's say now I told you, all of you have read about the biased random walk in the assignment, no? Right? What happens in the biased random walk? The probability of jumping to right is P, probability of jumping to left is Q. Is that right? Okay, now if that happens, can you just redo all the steps? Could that be an exercise for you all today? Is it too hard? Can you give it an attempt?
Yes.
Huh? Okay. So basically, I'll tell you all right away. There is this probability jumps delta x. No, half is there. No, this now one of them will become p, the other becomes q. It doesn't become half and half, it becomes p and q, which means that some of the steps here, the cancellations don't happen nicely. Okay. But I have given you all the machinery. Okay. And if you go to the canvas, you should be able to open the notes, right? And the notes will have all the steps anyway. You know, you will be able to, because it automatically syncs. So you must also have access to notes to cross-refer what, you know, basically P is equal to Q is equal to half is the scenario when there is no bias, there is an unbiased random walk, the current, whatever I have just shown you. But I just wanted to consider the case of them not being equal to half. And then just do derivation. And what we will find is not the diffusion equation. You will find some effect of the bias. And I want you to just redo it. There are two reasons why I want you to do this, although it's mathematical. The reason is that, you know, I hope that in the process we will actually think through each step a bit better, because you'll be doing it on your own now. And then you will have also solved a new problem. Okay. Is that fine? Will you try this? And in the meantime, I will have a small exercise for myself. What I will do is, you know, I told you this, right? This is the solution for diffusion equation. How I would like you to, I will try to make you an animation of how this, this distribution changes over time. Okay, that's my task. I will write a small R code and share it with you all, whereas you will do the analytical calculations. Is it fine? So I will start seeing you all in about half an hour. And if you want to take a short break, please feel free to do so. I know there are very few people. What we will do is we will form the groups the way it was done previously. But I can imagine that the number of people in each group will be really, really tiny, because there are only 18 people, including me and Arun, right? So maybe we can only do, I would say, maybe 4 people per group. What we will then do is I will just put you together based on who are all present. Okay. Is that fine? And there is no need for submission today. I will come to each group and we will discuss. So hi everyone, welcome back. So before I go forward, let me just tell you that in the solution for the diffusion equation that I wrote down on the Microsoft OneNote, I think the coefficients I probably must have gotten wrong. I think in the coefficient for the exponential term will have a pi in the denominator. I think I missed it. And whether you get 2 pi or 4 pi depends on whether you use 2d or d in your diffusion equation. I will make sure I will check that coefficients correctly and update the slides, you know, the one note later on. Okay. So with that caveat, so what I have done is very simple here. I want to plot how the solution of the diffusion equation for that initial value problem looks like. So what's the initial value problem? Remember that, you know, animal was at origin in the time t is equal to 0, right? And we want to know how does the probability now change over time, you know? Okay, so that's the basic idea behind this. So let me show you. So I'll just run this R code, very simple R code. I have just uploaded this. Can you see what's happening? So there's a time counter there. So what happened was that basically initially there was a concentration at 0, meaning we know the animal was at origin at time t is equal to 0, right? Meaning the probability was 1 at time t is equal to 0. And then now the probability diffuses because animal is now hopping around randomly. And now it is more likely to be found farther and farther. Now, how does that decay was actually shown by the video I just showed. I will actually make it a bit shorter, because nothing much happens after a while. So initially, that's how it looks. And then, so what you're seeing is not just a distribution that is static in time, but that is changing over time. That's really the most interesting part of it. And that this actually is a normal distribution. Is it clear now? Okay, cool. So that's what I wanted to have uploaded this. And by the way, if you ever want to do animations like this in R, it's really easy. All that what I have done basically here is that I have defined a function Okay, this P is the basically probability density function. Now you can see P is basically 1 over square root of 4 pi diffusion times T. Okay, I had missed this pi in my equation in one notes. Okay, and then we have exponential x square divided by 4 dt. I think I had gotten, the compared to what I wrote, there is a 2 pi that is different here, both in the exponential term and in the coefficient term. Okay, so I will confirm what is correct, whether this is correct or that is correct. I'll confirm later. So I have defined, I compute the value of P. Okay, and then I'm just plotting this P as a function of X. What is X vec? X vec is basically a sequence from -2 to 2 at an interval of 0.01. So for each value of X vec, there is a value of P. P itself is also a vector, by the way. It's again, for every value of X vec, there is a value of P, and that is given by the expression that I just wrote down. And I am plotting this versus this. The only interesting thing is the P depends on T. And there is a for loop in T. So as this for loop is running in T, P is changing, and I am plotting X versus P, which is changing over time. But here is the tricky part about R. Imagine I comment this thing, something called a sys.sleep 0.0. I've given some value there. If I don't do this, are you seeing the animation now? No, right? You're just seeing a static picture. Okay, the trick here is that, if you don't have, I'll just clear this, okay? If I just run this without the system sleep, this for loop, although there is a plot in every run of the for loop, it will plot only at the end. I think it didn't plot even that. Okay, I don't know why it refused to plot. Okay, now if the moment I say system sleep, the system must sleep for 0.1 seconds every time the for loop runs. Okay, if I do this, okay. So again, the trick is, you shouldn't give a very small time window to sleep. You should give a sufficiently large. Oh, what happened? Nothing is happening now. Even this is not showing. I don't know what happened. Plots. I think I have done something. Okay, for some reason, I'll just close the R and get back. Maybe there's something that I messed up. My trick has failed. Huh? Just close the R. Diffusion movie. Let me try again. I hope it doesn't shame me now. And follow my instructions. Can you see it now? Now it's working. There's some problem with R. The moment I have switched on sleep, it now works, right? Okay, that's the basic idea. So anytime you feel like making such movies, you have to use this command systems of sleep. I think there is also a command to, basically what you have is many different plots, right? You can also put them all to make a movie-like thing. I will see if I can find one of my codes that does it. But I'm sure you all know this better than me anyway. My tricks are probably at least 1 or 2 decades old now. Okay. Anyway, I just wanted to show you this. And as a follow-up to what I asked you all, to derive the revised diffusion equation when there is a biased random walk, if you are able to do that, what I would also like you to do is to derive, just make a guess, what should be the revised probability density equation. Right? Do you understand my question? So I showed you here, right? I claimed that solution for this is this equation, right? But now if there is a bias, how do you think this equation will change? Can you guess? Okay, so if you can guess, it's great. Otherwise, don't worry. You have to make guess based on the intuition. Don't think mathematically. If you are thinking of deriving mathematically, there is no way we'll get it, but just use your intuition. Okay. So that's all from my side. I'll now switch on the groups again. So go back and work. But I will have to leave by 4:45 or so. I have another meeting. Okay. So any questions on what I just showed you now? Okay, no questions. So shall I switch on the groups again? Okay. So stay as long as you want. I will make another visit around 4:45, and then after that we will close the session. Thank you.